Good morning, Year 10, and here we go again. So today we're looking at the resolution of forces. Another fun-filled physics lesson, I hear you say. Well, so today we've got 4 learning outcomes, and they go on a bit, but there they are on the screen. Happy reading. So, let's move on. So, quick quiz, 1 to 6 today. Quickly write down 1 to 6 in your margin, pause the slide, or pause the video, and answer the following 6 questions. So, basically question number 1, what effect do balance forces have on the motion of an object? If the forces are applied to an object of balance, then they have no effect. However, if the object is stationary, it will remain stationary. If the object is moving, it will continue moving in the same direction. Okay, then question 2. What effect may unbalanced forces have on the motion of an object? So basically, unbalanced forces will either make a stationary object start to move, it'll either change its direction, it could slow it down, it could speed it up. Okay? Alright, question 3. What does the size of acceleration of an object depend upon? The size depends on 2 things. First of all, the size of the force. The larger the force, the greater the acceleration, and the mass of the object, the greater the mass, the smaller the acceleration. You notice there that we've used and er statements. Make sure that we're including those, especially those people doing higher, because and er statements are the way forward. That's often what they're looking for in an exam. So, number 4, define the centre of mass. It is the point at which the mass is thought to be the most concentrated. Number 5, calculate the force needed to give an acceleration of 2 meters per second to a rock with a mass of 10 kilograms. 10 times 2, hopefully nobody needs a calculator for that, 20 newtons. Number 6, so state one difference and one similarity between speed and velocity. The difference is speed is scalar, velocity is a vector. Probably bored of hearing that one, but it comes up all the time. That's why we're going over and over it. Remember, practice makes permanence. Number 6, part B, similarity. They both have the same unit, meters per second. So moving on to today's lesson. So looking at the resolution of forces, we're going to be looking at how we can resolve the various forces acting on an object when it's not on the flat. So here we've got a cyclist cycling uphill, and it's actually anybody who's ever tried to cycling uphill, it is more difficult than cycling on a flat road, and there is a reason for that. The weight of the cyclist hasn't changed, but it's the effect of the forces acting downhill, and we need to look at how we can understand that and resolve those forces. Now, at this point, I suggest if you haven't already got one, can you go and get a protractor, ruler, pencil, and you will need some scrap paper. If you're just sitting there watching this on your bed, it will help you if you are doing this as we go along. So, to understand the downhill effect of the weight of the cyclist, consider the person as a box on a slope. You don't need to draw the cyclist, just draw them as a box, okay? And after lockdown, we're probably all going to be a bit box-shaped anyway. So, the force of gravity on the box can be seen on the left, and we can see the force of gravity. Now, gravity, remember, acts perpendicular to the Earth's crust. So, it's my red line, okay, acting through, down, from box, which is 0 to B. It can be split into 2 parts. We've got weight and we've got perpendicular component. So what we then do is make a parallelogram. Now we looked at parallelograms yesterday. However, today we're looking at resolving the forces using a parallelogram. Now we're going to resolve the force using 2 components. All right. I'm going to move on. You ready? So, for example, in the diagram of a toy trailer below, when a child pulls on the handle, some of the 5 Newton force pulls the trailer upwards, up from the ground, and some of it pulls it to the right. Okay, The vector diagrams can be used to resolve the pulling force into a horizontal component acting to the right and the vertical component acting upwards. So we've got an angle of 37 degrees. Now remember, because we're drawing this to scale, the size of the arrow needs to be proportional, and that's really important. It needs to have a scale. Otherwise you're going to get yourself in a tiswas. Okay, make sure that you use a protractor to draw that and use a scale of maybe 1 Newton equals 1 centimetre. So this is how we're going to resolve it. So you draw a right angled triangle to scale in which the side of it represents the force. Try to choose a simple scale, e.g. 1 centimetre equals 1 Newton. It's like I read the slides before, you know. For the toy trailer, for example, draw above the line representing the 5 Newton at 37 degrees. A horizontal line ending directly below the first line. A vertical line between the ends of 2 lines, arrowheads, show the direction in which the forces act. The child's pulling force can be resolved into a 4 Newton force and the 5 Newtons upwards. Okay, happy with that? Excellent. And we're using Pythagoras. You can use Pythagoras theorem, but you can also do it just by measuring scale. All right. So it's defined as the process of splitting up given the force into a number of components. It's called the resolution of a force. Okay. There is another YouTube video for you to watch to explain how to do this in more detail. I have added this to the clips at the bottom. Okay. Right. So watch the video and have a go now at how to resolve this force. So a box is resting on a 30-degree incline. To resolve the force into parallel and perpendicular components, the box has a weight of 50 newtons. So we've drawn the weight on with a nice green arrow, and we can see here that this arrow is acting perpendicular to the Earth's crust. And you also notice that that comes from the centre of mass. Okay. First of all, we draw a parallel line. Okay, then second part, we draw the perpendicular line. Then we draw a line between the end of my 50 Newton weight line to my perpendicular line to make a right angle triangle. Then I join upwards to the first initial line, okay, to make a parallelogram. We can then measure the length of the perpendicular line to make 8.8 centimetres. And because 1 centimetre equals 1 Newton, we know that the perpendicular component is 8.8 times 5. The parallel component is 4.8. Which gives me 24 newtons. All right. So we need to think about equilibrium. We did touch on this when we looked at centre of mass. So equilibrium is when the forces are acting on an object are zero. All resultant forces add up to zero. And when all the resultant forces add up to zero, then actually the object doesn't move, or it continues to move with no change of direction. Okay. When the lines of action of forces are parallel and some of the opposite forces are equal, tick, we know that. And also when the lines of action and the forces are not parallel. Now you'll notice within this text there is lots of highlighted words, and you need to be really careful because, as I've said, 40% of the paper is marked on the mathematical ability alone. However, some of it is what we call keyword marked. I would suggest you pause this slide and you underline the words in bold in your notes so that you've got those, and make sure that you're happy with what those words mean. Okay? So let's talk about equilibrium. Nearly said it completely wrong. So in this example, the box is at equilibrium. It means it's sitting on my slope and it's not moving. We've got the friction, okay, acting between the surface of the box and the slope. we've got weight, which is acting from the centre of mass upwards, and we've got the reaction of the slope on the box. So they're my three forces that I'm going to draw onto my diagram. You'll notice that my arrows are all different lengths, which indicates that all the forces are of different sizes. They don't make the mistake of drawing, because it's at equilibrium, drawing them all at the same size, because weight is added between the friction and the reaction. So the box is in equilibrium, it's balanced on the slope, which means the angle of the forces are equal. So we've got Fn, Ff, Fg, okay? Now this slide seems to have come up funny here, so what I'm going to just quickly make sure. You can work out the weight as long as you know the normal reaction and friction. Alright, so we've got to use the equation. Let me just flick through my notes. Here we are. Excellent. So we're going to try and work out that using these objects, and we do need a scientific calculator. If you haven't got one, you need to go and grab one now, okay, because we're going to use cos and sine to calculate these. As long as you draw the resultant vector to scale, you can work out, and at the angle, you can answer all these questions using scale drawings. So a student pushed a trolley of 510 newtons up a slope, and that is inclined at a 15 degrees to the horizontal. Determine the component of the trolley's weight down the slope. So the answer is 132 newton. A box of weight is at rest on a slope. The slope is at an angle of 30 degrees to the horizontal. Copy the diagram and determine the components of the box's weight in the parallel perpendicular to the slope. It's worth 3 marks just for some maths here. Okay, so we draw a line parallel, a line perpendicular. We then make my parallelogram to scale, and then times up whatever it is the scale that you've used. Okay, so resolving force, key points. So basically, it means you need to find the perpendicular components that have a resultant force that is equal to the force, resolve the force in two perpendicular directions, draw a rectangle with adjacent sides along the two directions so that diagonal represents the force vector, and for an object in equilibrium, the resultant force is 0. An object at rest is in equilibrium because the resultant force on it is 0. I suggest you pause the slide, copy down those key points. Okay, the task associated with this is shown on Show My Homework. Thank you, bye.